Now our next question is to understand that to really just mathematically establish the relationship between the independent set and vertex cover, and then with this relationship we can sort of go through a concrete example of the reductions, right? So the quiz here again, I try to highlight this idea, right? So we are given another arbitrary graph, right? So we already know that it's obviously the set of black nodes form an independent set, right? So independent set means that if I look at any pair of nodes in this among these three black nodes, like they don't form an edge, right? So now if the black nodes are independent set, so the complements, which are all the white nodes, then we can believe that it's a vertex cover, and then we can sort of verify again on our own that it's indeed true for any edge, right? So at least one end of the edge is a white node, right? So if I look at this edge, one end is white node, right? If I look at this edge, both ends are white nodes, right? So it's indeed again that our summation remains true for another graph, right? So the vertex cover, we find a vertex cover of size 7 and another independent set of size 3, right? So C is correct, right? So I think we are sort of running out of time. At least we won't be able to finish the entire the proof for the between to establish the relationship between the independent set and vertex cover. So we're going to leave that in the next lecture. So again, I'm sorry that this lecture was not uploaded on time. So the next lecture will be uploaded within a day or two. And talk to you. So now let's examine the independent set, right? So this is roughly speaking the packing part of the problem, right? So in the independent set problem, we are given a graph, right? This is undirected, unweighted graph that consists of the edge set and vertex set, and an integer k. And our question is to ask that whether there is a subset of size k, subset of k vertices such that no two are adjacent, right? Right. For instance, if we look at this graph, right? So basically we want to let's say that we want to ask a very specific, a very concrete question, right? Is there an independent set of size 6, right? So again, so the independent set means that I find a subset of vertices, right, such that for any two vertices in the subset, we are not expected to see the edge, right? Right. So this is the definition of the independent set, and the independent set question is that are we able to find a subset of a specific size, and so that this subset is independent set, right? So this is let me just annotate this text a little bit, right? So if we have a subset S of vertices such that no two vertices are independent, this set is called the independent set, right? Set, and this is also the mathematical definition here. And the question, independent set question here, it's really literally asking us to understand whether we are able to find a subset of size k of independent set, an independent set of size k, right? So now this is the first concrete question, right? Whether we can find an independent set of size 6, right? So if we use this graph as an example, right? So let's just redraw the entire graph, right? So if we have a graph that looks like that, right? So before having the coloring the graph, right? So and let's also draw the edges, right? So be careful. Let me just draw all the edges, right? So there was an election yesterday, so I was a bit stressed, and so it's getting so it's very getting a little bit harder for me to draw things clearly, right? So so what we are doing here is that we start with drawing a picture, a graph. Actually, that's exactly a replication of what's known here. And our question is to understand whether we can find an independent set of size 6, right? So let me just give you some example of independent set, right? So the first example of independent set will be this two, right? So this one, like if I call this one A, this one B, then the subset of A and B is an independent set, because if I look at the edges that I look at the AB, right, the relationship between A and B, and then I know that there's no edge that's connecting between A and B, right? For the same reason, if I call this node C, and then also include the C in our set, right? So this set is also independent set because AB is not an edge, right? BC is not an edge, right? And AC is not an edge, right? So this is also an independent set, right? Let me also give you an example that's not an independent set, right? So not an independent set really means that if we let the D to be here, right? So if we have this all three nodes, right? So if we have ABD, right? So this is not an independent set. Independent set, right? Why is that? Because BD is an edge. BD is an edge, right? So now the question is that, is there a way to find an independent set of size 6, right? So it turns out that if we select this black nodes, right, all these nodes, and we call all these nodes, right, aggregate them together and call that S, right? Let me just make it a little bit bolder, right? So if we call that S, then basically this S is independent set, because obviously if I look at all these black nodes, there's no edge at all that's connecting any black nodes, right? So we managed to find an independent set of size 6, right? But it turns out that we cannot find any independent set of size 7, right? So you can try to play around this graph on your own, but it turns out that it's just the largest possible independent set is exactly 6, right? So for instance, if we want to add a new node here, then obviously we there's an edge that's connecting the black one and the new node, so it's not an independent set, and then we can try other nodes, right? So we can also even try to delete some of the nodes and try to add more nodes, but you will just figure out that like 6 is the max possible one. Right. So this is the first problem we look into, the independent set, right? So again, so where we are heading is that we sort of want to highlight a very concrete idea of the reduction, right? So we sort of want to give you an example of the two problems, X and Y, and X is reducible to Y, right? So this is the first problem, right? The X problem, right? So we sort of now want to move to the Y problem, right? So now the Y problem we are working at here is the vertex cover problem. So for a vertex problem, the definition is as follows. If we are given a graph G equals to V and E, and also an integer, and we sort of want to understand that whether there's a subset of K vertices such that each edge is incident to at least one vertex in the subset, right? Let me also just explain this definition in details, like what we did in the independent set, right? So if we have a subset of K vertices such that each edge is incident to at least one of the vertices in the subset, then this subset is called the cover set. Cover set, right? So let me just make this a little bit thinner, right? So this is the cover set, right? So let me just give you an example, right? So if I only have this graph like this, right? So let me draw things in this way, right? So this is the graph we have, right? So let me give you an example of the cover set, right? Vertex cover set, right? So this is A, B, C, D. So the claim here is that the A, B, C, D, A, B, D is a cover. Right. why is that? So I can also look at all the edges here, right? E1, E2, E3, E4, right? I have a total number of 4 edges here, right? So the statement here is that if I examine an arbitrary edge, we know that it's incident to at least one vertex in the subset. Say, let's start with examining E1, right? So E1 is connecting between A and B. We know that both A and B are inside the set we select, right? So basically we sort of have the condition is held here, we have a check here, right? So, and we do the same thing, right? So we look at E2, right? It's A and D, and A and D are both into this set. So right, E2 is also good. And then if you look at E3 and B and D, it's also good. All right, the only a little bit more interesting thing is in B and C, right? So while C is not in this cover, we know that B is in this cover, right? Right. So now if I look at the problem, if I look at the instance we were looking into just now, right? So this is the graph instance here, right? So now if we instead of asking us to find the independent set, if we want to find the vertex cover, like what would be an example of vertex cover? And it turns out that if we just look at the white node here, right? The white node here. Now let me again use a bit bolder things, right? So if I look at all this white node, and then if I call this whole things as S, then S would be the vertex cover, right? So we can also just double check that, right? So if I look at just double check by looking at every edge, right? If I look at this edge, it's connecting to one of the vertex cover node, right? Yeah, so let me just change the color to the purple one, right? So if I look at this edge, it's connecting to a node into the cover set. If I look at this edge, again, it's connecting to both nodes are in the cover set, right? So regardless which edge I look into, there's at least one side of the node is inside the cover set we defined here, right? So let me just erase everything and then just make it look a little bit cleaner and just re-emphasize the idea, right? So the vertex cover set, we claim that can be one possible vertex cover set can be this one. Right? So this would be our S, and then which is the vertex cover set, and let's verify that. Let's just check us every single edges. If I look at this edge, right, one side of node is inside S, right? So if I look at this edge, both are inside the S, right? So regardless which edge I look into, right? So if I look at this edge, right, the node, the one, at least again, the left side of the node is in S, right? So the point here is that regardless which edge we have, right, we can check that at least one node of the edge connects is inside S, right? So in this case, right, we can confirm that the set of Y node is actually a vertex cover, right? So now what's interesting is that the black nodes in this example is an independent set, and then the Y nodes here, right? All the nodes that are not black actually form a vertex cover, right? So if we take the union of the independent set of the vertex cover, it's actually the entire all the vertices, right? Right. So the question is that is it a coincidence or is it just in general this kind of observation and relationship is true, right? So we sort of want to understand, is it really true that for any independent set, if we take the complement, it will just be the vertex cover, right? So say that independent set. So say that if we have if we look into this as an example, right? So if we can draw this one as we use A and C to be one independent set, right? So and then if I look at all the complement, right? So which is B and D, right? The question is that is it B and D a vertex cover? A vertex cover, right? And So right, if you check all the edges, it's actually surprised you a little bit, right? So B and D indeed is a vertex cover. It seems that this is really just indeed is true, right? So it seems that this is really it could be a very very general observations we are seeing here, right? So long as we manage to find one independent set, we look at the complement, then it's a vertex cover. So now, why do we care about the reductions, right? So there are three main reasons we do care about the reductions, right? So, when I say care about the reductions, then why do I want to establish that y is x is reducible to y, or the other way around, right? Um, so so basically, there are three reasons, right? The first reason is that if we are able to the first reason is that we can design algorithms, right? So say that we have already an algorithm for solving y. Say we have an algorithm for solving the max flow, and we face a new algorithm problems, right? So we have never seen this algorithm problem before, right? But if we somehow manage to show that x is polynomial time reducible to y, right? And we also know there's an algorithm for solving y, then basically we indirectly construct an algorithm for solving x, right? So this is the first utility of establishing this reduction, right? So if we have an algorithm for y, then we will automatically have an algorithm for x when we establish the reducibility between these two problems, right? So now the second problem is to the second reason to establish the reducibility is the establish the intractability, right? So what does that mean? If we are able to show that x is reducible to y, and we also can show that x cannot be solved in polynomial time, then we can also know that y cannot be solved in polynomial time, right? So basically, it's really just that if we already know one instance is hard, right, the x instance is hard, and if we are also managed to establish that the instance of y is even harder than x, then we are able to say that y is also a very hard problem, right? So this is how we manage to really build the zoo of problems, and then starting from some of the very simplest, some of the very standard hard problems, and gradually expand the rule, right? So in the field, so then when you tackle a new algorithm problem, basically what you need to do is really just to revisit the rules people have built so far, right? So all these kind of existing reductions, and see whether there's any animals or any problems in the rules that's already known to be NP hard, and and then try to connect these known NP hard problems with the problems on your hand, and determine, and it helps you to determine whether your problem is also hard, right? So somehow I saw the forward references the so-called NP hard problem, right? So NP hard problem, right, as we will see in the next few lectures, it's really just the set of problems that are very unlikely to be solvable in polynomial time, right? So it's really just a computer science formal way to describe this problem is hard, right? So this is the second utility, that if we know one instance is hard, and then we are able to produce the reduction relationship, that we will know another instance is also hard, right? Finally, we can also establish the equivalence between two problems, right? So if we know both x is not, it's easier than y, and y is easier than x, right? So computationally, right? So we can just directly say that these two problems are the same, right? Effectively the same, right? In terms of the mathematical notion, right? So basically it says that x can be solved in polynomial time if and only if y can be solved in polynomial time, right? This bottom line really summarizes what we have been trying to emphasize for the entire call, the entire lecture, very precisely, right? So the reductions helps us to classify problems according to the relative difficulty, right? So if we can say that one problem is easier than another problem that can already be solved, then the easier problem can also be solved, right? And if we can say that one problem is harder than another problem that's known to be intractable, then we also know that the new problem, we found a new hard problem, right? So it's all about the relative difficulty. Right. So now let's be concrete and talk about one specific reduction in this class, and we are going to go through a lot of this kind of reductions for the next 3 lectures. Right. So the reduction we are talking about here is that we look into the packing and the covering problems. Right. So now so we need to sort of introduce the notion of the independent set in order to sort of move forward our discussion.